Welcome to this explainer. Okay, today we're stepping into what is essentially a masterclass on one of organic chemistry's most famous and, honestly, most foundational rivalries. We're going to look really closely at the SN1 versus the SN2 reactions. Now, if you've ever felt completely overwhelmed by organic chemistry pathways in the past, don't worry. We're going to break this down step by step. By treating this as a structured lecture, you're going to see just how elegant and surprisingly predictable these microscopic interactions truly are. So let's just dive right into it.
Here's our quick roadmap for this session. 1. The dilemma. 2. SN1, the patient pathway. 3. SN2, the backside attack. 4. Comparing substrates and nucleophiles. 5. Solvents and stereochemistry. And finally, 6. Choosing the right pathway. By the end of this explainer, you're going to have the exact rules you need to predict these crucial chemical pathways with total confidence.
Section 1. The dilemma. Before we get into the weeds of the pathways, let's just make sure we're all starting on the exact same page. What actually is a nucleophilic substitution? Well, at its core, it's simply a reaction where a chemical species that has an available electron pair, which we call the nucleophile, replaces a leaving group on a target molecule, known as the substrate. Think of it like a microscopic dance, right? One partner taps in and the other steps out.
And this perfectly illustrates the entire landscape we're exploring today. This is basically our master blueprint, our ultimate cheat sheet. When that nucleophile looks to replace the leaving group, the reaction can proceed down one of two very distinct, highly competitive pathways. You've got the SN1 pathway or the SN2 pathway. Throughout this explainer, we're going to dissect every single element of this blueprint.
Section 2. SN1, the patient pathway. Formally, SN1 stands for Substitution Nucleophilic Unimolecular, and that 1 in SN1 is incredibly important. It literally stands for unimolecular. This means the molecularity is 1, and the rate law of the entire reaction, basically how fast it goes, depends entirely on just one molecule, and that's the substrate. The nucleophile's concentration, it doesn't affect the speed at all. It's almost as if the reaction is just sitting there, patiently waiting for the substrate to make the first move, all on its own.
And here's exactly how that patient, unmolecular mechanism works in reality. It happens in two distinct steps. Step 1 is the slow step. This is where the substrate undergoes ionization. The leaving group just attaches on its own, forming an intermediate called a carbocation, denoted as R+. Because this step is so slow, it dictates the speed of the whole shebang. Once that carbocation is finally formed, boom, we move to step 2, which is fast. The nucleophile spots that positive charge and immediately attacks to form the final product.
Moving on to Section 3, SN2, the backside attack.
So, if SN1 was the patient pathway, just waiting around for the leaving group to leave, SN2 is the complete opposite. It's impatient, it's direct, and it's defined by a highly aggressive maneuver. Here, the 2 means bimolecular. Unlike SN1, the rate law for an SN2 reaction depends on the concentration of both the substrate and the nucleophile at the exact same time. They are both actively involved in the single rate-determining step of the reaction.
Now, what's really wild is how much this contrasts with our previous pathway. The SN2 mechanism is a one-step concerted reaction. There's zero waiting around. The nucleophile literally forces its way in from the back of the molecule at the exact same time the leaving group is being shoved out from the front. Because it all happens in one dramatic, synchronized step, absolutely no carbocation intermediate is ever formed.
Section 4. Comparing substrates and nucleophiles.
Okay, so we have a two-step patient pathway and a one-step aggressive pathway. How do we actually know which one is going to happen? Well, first, let's look at the order of reactivity for the substrate. They are exact opposites. For SN1, it strongly prefers tertiary substrates, that's the 3 degrees, followed by secondary, then primary, and honestly, it almost never happens with a simple methyl substrate. Why? Because SN1 desperately needs to form a stable carbocation, and tertiary carbocations are by far the most stable. Now, conversely, look at SN2. It prefers the methyl substrate, CH3X, above all else, followed by primary, then secondary, and almost never tertiary. Because SN2 relies on that concerted backside attack, it needs a physically open, uncrowded molecule to actually allow the nucleophile to get in there.
Next up, let's compare the nucleophile requirements. Because the SN1 rate only depends on the substrate slowly forming an intermediate, it really doesn't matter how strong the nucleophile is. A weak nucleophile is perfectly fine, things like plain water or alcohols like ROH. But that aggressive SN2 pathway, it absolutely demands a strong nucleophile to force the reaction immediately. It needs a powerful species with a strong negative charge, like hydroxide, cyanide, or an iodide ion to execute that backside attack effectively.
Section 5. Solvents and Stereochemistry.
So the substrate and the nucleophile give us these massive clues, but we absolutely can't forget about the environment they're swimming in. The liquid solvent you choose actually stabilizes different parts of these reactions. For SN1, you want a polar protic solvent. These are solvents capable of hydrogen bonding, like water or alcohols, which really help stabilize that charged carbocation intermediate. On the flip side, SN2 requires polar aprotic solvents. These are solvents that lack hydrogen bonding, like acetone, DMSO, or DMF. These solvents don't trap or cage the nucleophile, leaving it highly reactive and perfectly primed to launch its one-step attack.
And then there's the stereochemistry, which is essentially the 3D physical outcome of the molecule. For SN1, because that carbocation intermediate is totally flat, the nucleophile can attack from either the front or the back. This results in racemization, meaning you get a mixture of molecules with both inversion and retention of their original shape. But for SN2, remember that backside attack? Because the nucleophile only comes from the exact opposite side of the leaving group, it forces a complete inversion of configuration, which is also known as a Walden inversion. Think of it exactly like an umbrella blowing completely inside out in a massive gust of wind.
Section 6. Choosing the right pathway.
All right, we have covered a ton of ground here, dissecting the mechanism, substrate, nucleophile, solvent, and 3D structure. So, if you're staring at a chemical equation, how do you ultimately predict the outcome? I want you to treat this quick summary as your ultimate exam prep checklist. It beautifully compiles everything we've found. Let's trace it down. Steps: SN1 takes 2 patient steps. SN2 takes 1 concerted step. Carbocation formed? Yes in SN1, absolutely no in SN2. Because of that carbocation, is molecular rearrangement possible? Yes for SN1, no for SN2. Stereochemistry? SN1 gives you a racemized mixture, SN2 gives you a clean, inside-out inversion. And finally, the rate. SN1 is unimolecular depending only on the substrate. SN2 is bimolecular, depending on both the substrate and the nucleophile.
So the absolutely crucial takeaway is this golden rule of thumb. Choose the pathway based on substrate, nucleophile, and solvent. If you have a tertiary substrate sitting in water, you know for sure you're looking at SN1. If you have a primary substrate paired with a strong cyanide nucleophile in acetone, you can confidently say it'll be an SN2 backside attack. It really is that logical and completely rule-based.
I want to leave you with this thought to ponder. We just explored how these totally invisible split-second dances of molecules strictly dictate the physical chemistry of our universe. Knowing this, how might a chemist altering just one simple variable, say scratching water and swapping in acetone as a solvent, change the entire 3D architecture, and therefore the effectiveness of a life-saving drug? The choices we make on the microscopic scale echo incredibly loudly in our macro world. Thank you so much for joining me in this explainer, and keep exploring.